So in the last lecture, we studied about what is the output of a second order system when the input is a unit step. And then we studied about some important remarks on that how we are going to use that particular equation if the input is unit step function. In place of unit step function, it has a certain amplitude. And what will be the effect corresponding to that on the output? So in this lecture, we are going to study about the transient response specifications. So I'm going to start this lecture. Transient response specifications. So before starting this one, if you have any doubt related to the previous lecture, you can ask me. Okay. This is a function of time, then there is an output CT, and this one is 100%. This one is 100%. Now we have a waveform, output response. Now so this one is 98%, this one is 102%. Now there is a 90%. There is a one spot for 50% and one for the 10%. So first concept that we are going to study is delay time. TD. It is the time required for the response to 50% of the final value in the first attempt. Means first time when it reached 50% of the final value in the first attempt. And it is given by time delay TD is equal to 1 plus 0.7 times zeta upon omega n. As you know that zeta is a damping frequency, damping factor, and omega n is a natural frequency. And 50% of its final value in its first attempt. So this one is TD. So that time is known as time delay or delay time. We are going to drive this one in the later part of the lecture. So, but first we are going to understand what it stands or what it states. Now the next point that we are going to study is next point is rise time. Rise time, that is TR. It is the time required for the response to rise from 10% to 90% of the final value. Time required for the response to rise from 10% to 90% of the final value. For over-damped system and 0 to 100% of the final value for under-damped system. So it means if we are going to consider an over-damped system, we have to measure the time from 10% to 90%. And if we are going for under-damped system, we are going to measure the time that is required to reach it from 0 to 100% time response, or 10% to 90% for the over-damped system and 0 to 100% for under-damped system. And if we are going to represent it through a formula, then it is T rise is equal to pi minus theta upon omega d. T rise is equal to pi minus theta upon omega d. So now you understand what is omega d. Omega d is a natural frequency. And what is theta? Theta is tan inverse under root of 1 minus zeta squared upon zeta. One thing you have to remember that this theta is in radian. Because pi is in radian, so we have to subtract theta from it. But before taking this one, we have to convert theta into radian. If it is in degree. And omega d, you know that it is a damping frequency, which is nothing but omega n under root of 1 minus zeta square. So this one is a rise time. Now we are going to discuss about peak time. Oh my God. Hello. Hello. Vaibhav. वैभव।
यस सर।
मेरी आवाज आ रही थी बेटा इससे पहले कि नहीं?
हाँ जी सर आ रही है, थोड़ी सी लैग हो रही थी बस।
नहीं इससे पहले
बीच में हुई थी थोड़ी सी लैग हो रही थी थोड़ी सी।
ओके वो तो इंटरनेट का इश्यू है बट आवाज आ रही थी।
हाँ सर आ रही थी।
Now next one is peak time. What is peak time? So this peak time, it is the time required for the response to reach its peak value. So response to its peak value. So maximum peak is going to be obtained at this position. So this time is known as peak time. So if we are going to consider this time is nothing but peak time. Okay? Now there is another definition for this one, that it is also defined, ये point ध्यान रखिएगा, as the time required at which response undergoes the first overshoot. Which is always peak overshoot. So as you can see in this figure that they are at different overshoot. This is also another overshoot. So we cannot take this time as a peak time because its definition states that the first overshoot time, we have to take the first overshoot time. So this time cannot be taken as a peak time. Peak time is corresponding to the first overshoot. And the first overshoot that we are going to obtain is this one. So this is the peak time. But in some question, if I am going to mention you that you have to calculate a second overshoot time, then you have to mention me this time. So how we are going to calculate the second overshoot time, we are going to discuss later on. But in general, the peak time is known corresponding to the first overshoot. And the formula corresponding to peak time is Tp is equal to pi upon omega d. Omega d is a natural frequency which is equivalent, damping frequency which is equivalent to omega n under root of 1 minus zeta square. Here always zeta is less than 1, so it means it's an underdamped system. Now, the another point that we are going to learn through this plug is peak overshoot. This one. The next point is peak overshoot. It is the largest error between reference input and output during transit. So largest error between the reference input and the output. So this is an output performance and this one is a reference one. This one is a reference one that we need in 100% and this is an actual output and the largest error is this one. So this is known as peak overshoot, which is denoted by MP. And MP is known as your output is CT, and if we are going to consider CT, output is CT, and when we are going to obtain this one at rise time, at peak time, this one is TP. So we have to mention it here. This one is TP. So when we are going to obtain this one, when T is equal to TP, then CT is nothing but this one. And we have to subtract a reference which is 100% or 1. So this is MP. ये point clear है? Because our input is a unit step function. So we are going to consider here 1. And the CT at TP, at T is equal to TP, we are going to get this one. Now if we are going to solve this one, we are going to get e to the power minus pi zeta under root of 1 minus zeta square. And if we are going to consider it into a percentage, then we are going to write this one. MP percent is e to the power minus pi zeta under root of 1 minus zeta square into 100. So this one is a peak overshoot. So we are going to find out all these expressions through CT. And that we are going to discuss in the later part of the lecture. Now the next point is settling time. So what is settling time? That we had already discussed though. Settling time. Time required for the response to decrease for the response, that is CT, to decrease and stay within a specified percentage of its final value. Its final value. So settling time is the time required for the response to decrease and stay within the specified percentage of its final value. For example, specified percentage is plus minus 2%. So here you can say that it goes to 100% to 102%, or it is reducing from this to this one, 98%. So plus minus 2% this one. So when we are going to achieve this one, we are going to achieve here. When it is within the specified range, this one. Either it is plus certain error or it is minus certain amount of error, which is specified by you. It can be plus minus 2% or it can be plus minus 5%. And that is going to be defined by the user. So when we are going to reach that limit, that time is known as settling time. So this one is TS. Now the last one is time constant. That time constant is the time required. Sorry, settling time we have to define first. That settling time TS is 4 times time constant. That settling time is nothing but 4 times time constant. What is time constant? Is the time required by the system output to reach 63.2% of its final value during first attempt. So 63.1% something we are going to attain here. So this is known as time constant. That is capital T. Now, this time constant or this settling time can be equivalent to 4 times 1 upon zeta into omega n, and this time constant is nothing but 1 by zeta into omega n. So how we are going to obtain this one? We are going to discuss this, but you have to remember all these basic concepts. That what is time delay? To achieve 50% of its final value is nothing but time delay. To reach its first maxima is known as peak time, and the amount of error between the reference and the output is nothing but a peak overshoot, and the time required to reach the system from 0 to 100% is known as rise time for underdamped system, and 10% to 90% for overdamped system, and to reach within a specified percentage of its output, that is defined by the user, that if it is plus minus 2%, this is known as settling time. And that settling time TS is equal to 4 upon zeta into omega n. That is plus minus 2%. Now, if we want to drive all those things, how we are going to do that one? Now we are going to study that one. First one is peak time, TP. So as you know, the output response CT is 1 minus e to the power minus zeta omega n t upon under root of 1 minus zeta square, and this one is sine of omega dt plus theta. where theta, you know that tan inverse under root of 1 minus zeta square upon zeta. So as you know, at t is equal to tp, ct क्या होता है? ct will achieve its maxima. Its maxima, as you can see from this figure, that at t equal to tp, ct is going to be achieve its maxima. So we are going to divide dct by dt at t is equal to tp. It will always equivalent to 0. So now if we are going to differentiate ct, it is going to be 1 will become 0, e to the power minus zeta omega n t upon, and this will come zeta minus omega n, then this one is sine of omega dt plus theta. First I took this one as a we are going to differentiate, and this one is a constant, upon under root of 1 minus zeta square, and then we are going to take this one as a variable and this one as a constant. So this will become e to the power minus zeta omega n t upon under root of 1 minus zeta square, and this will become omega d cos of omega dt plus theta. Now we have to equate this one equivalent to 0. So what we are going to get? Zeta omega n e to the power minus zeta omega n t upon under root of 1 minus zeta square sine of omega dt plus theta is equal to e to the power minus zeta omega n t upon under root of 1 minus zeta square. Here we are getting omega n, so we can write omega n under root omega d 1 minus zeta square cos of omega dt plus theta. Now if we are going to solve this one, so zeta sine of omega dt plus theta minus times under root of 1 minus zeta square cos of omega dt plus theta, which is equivalent to 0. Or we can write that tan of omega dt plus theta is equal to under root of 1 minus zeta square upon zeta. And you know that theta is nothing but tan inverse under root of 1 minus zeta square by zeta. So we can write it here that tan of omega dt plus theta is nothing but tan of theta. Now tan, there is a one property that tan n pi plus theta is nothing but tan theta. So from this property, where n is equal to 1, 2, 3 dot dot dot, we can say that omega dt is nothing but n pi, and here t is nothing but tp. So tp comes out to be n pi by omega d from this one. Now what you can say that Tp is n pi by omega d, where n is 1, 2, 3 dot dot. When n is equal to 1, it will give you first peak overshoot. When n is equal to 2, it will give you second peak overshoot. So in general, what we studied for first overshoot, Tp is nothing but pi by omega d. But if we want to calculate what is second overshoot time, then this is nothing but 2 pi by omega d. This time is nothing but 2 pi by omega d, this Tp. Till now, if you have any question, please ask me. Gavita?
No, sir, no doubt.
So everything you can derive from that particular equation. So now you have clear that if I am going to ask you second overshoot, how you are going to find it out. Now, what about MP? That is a peak overshoot. So as I told you, MP is nothing but CT when T is equal to TP minus 1. So what is CT?
Sir, can you show the previous slide?
Yes. This is corresponding to this one. For second overshoot, TP comes out to be 2 pi by omega d. For third overshoot, it is TP is 3 pi by omega d. And you know that omega d is nothing but omega n under root of 1 minus zeta square. Clear hai?
Yes, sir.
Now peak overshoot. So we are getting a first overshoot when T is equal to TP. But before that we have to write CT. What is CT? E to the power minus zeta omega n T upon under root of 1 minus zeta square into sine of omega d T plus theta. When T is equal to PP minus 1. So now I am going to put the value of TP, which is pi by omega d. And 1 will be cancelled out. So e to the power minus zeta omega n. And what is TP? TP is pi by omega d. And omega d is nothing but omega n under root of 1 minus zeta square upon under root of 1 minus zeta square into sine of omega d, and TP is pi by omega d plus theta, and this one is minus sine. So if you are going to put minus sine e to the power minus zeta omega n, sorry, omega n is going to be cancelled out. So it will become pi by under root of 1 minus zeta square upon under root of 1 minus zeta square. And this will become sine of pi plus theta. And sine of pi plus theta is nothing but it is equivalent to minus sine theta. So now MP will become minus will be cancelled out, or plus zeta pi by under root of 1 minus zeta square upon under root of 1 minus zeta square, and this is sine theta. As you know, in the case of tan theta, under root of 1 minus zeta square upon zeta. So it means this is nothing but 1 minus zeta square, and this one is zeta. So this comes out to be 1. Now if I am going to put the value of sine theta, what it will be? Under root of 1 minus zeta square upon 1. From here you can say that sine theta is nothing but under root of 1 minus zeta square by 1. So this is going to be cancelled out. So MP will become e to the power minus zeta pi upon under root of 1 minus zeta square. If you want to represent it into a percentage, then you can multiply it by 100. Clear again? This under root of 1 minus zeta is an exponential term. कोई डाउट है इसमें? अंकिता जैन?
No, sir.
Now, for example, I have to find out what is rise time. So rise time for underdamped system is to reach it from 0 to 100%. So CT at T is equal to TR, it will become 100% or 1. So now 1 is equal to, and what is CT? 1 minus e to the power minus zeta omega n T, which is rise time, upon under root of 1 minus zeta square into sine of theta. So 1 will cancel out, and this is also going to be divided. So now it will become sine of, this is nothing but E rise, sine of omega d TR plus theta is equivalent to 0, and which is nothing but sine of n pi. Or you can say that omega d TR plus theta is nothing but n pi. Or you can say that TR is nothing but n pi minus theta upon omega d. So guys, time, first guys time, if we are going to consider it, then n is equal to 1. So it is going to be pi minus theta upon omega d. The only thing that you have to remember that theta is in radian and this time comes out to be in second. This one is guys time. Now next one is, what is settling time? So as I said that it is the user who is going to be decide that it is going for a plus minus 2% or you are going for plus minus 5%. So you can say that CT at t is equal to TS is nothing but 0.98, that is 98%. If I am going to consider it minus plus minus 2%. So if we are going to consider minus 2%, then from in place of 100% it is 0.98. Now you remember that, as you can see in this figure, that when I reaches to the transient time, then this oscillatory nature is going to be die out. Now it becomes non-oscillatory. You can see here. Before that, there is a oscillatory nature of the output. But after the transient time or just at the transient time, that oscillatory nature is going to be vanished. So CT at t is equal to Ts is nothing but 1 minus e to the power minus zeta omega n Ts, and that oscillatory term we are going to remove it. So the only term which we control the amplitude of the output plus minus 2%, we can write it. The only term which control the amplitude of the output within plus minus 2% is e to the power minus zeta into omega n Ts, because the transient oscillatory form is completely vanished when t is equal to Ts. So now we are going to equate this one, that 0.98% is nothing but 1 minus e to the power minus zeta omega n Ts, and this will become minus zeta omega n Ts is equal to ln of 0.02, and if we are going to solve it, this will come out to be 3.92. So Ts is nothing but 3.92 upon zeta into, sorry, omega n into zeta, and if we want, we can also approximate it into zeta into omega n for plus minus 2%. Similarly, if we are going to solve it for plus minus 5%, that is 95%. If you are going to put it, then we are going to find settling time is nothing but 2.99 upon zeta into omega n, and that is equivalent to 3 upon zeta into omega n, where t, which is time constant, is 1 by zeta into omega n. So you have to remember that for plus minus 5%, that settling time comes out to be 3 upon zeta into omega n, and for plus minus 2%, it is 4 upon zeta into omega n. Clear है सबको? सात्विक गोयल,
Yes, sir.
कुछ डाउट है?
No, sir.
Okay. So you have to go through this video and find out the derivation of all the times or transient response of the control system. So we have studied in this chapter what is a steady state error, static coefficients, steady state error coefficients, that is Kp, Kd and Ka, and then we studied about different type of time responses. For example, peak time, rise time, then delay time, time constant, peak overshoot value. So you have to practice it on. Or I have an example. Okay. I'm going to solve an example for you. For example, I have a transfer function which comes out to be 8 upon s square plus 4s plus 8. Now, you have to calculate the transient response of the system. If I'm going to say you that you have to calculate the transient response of the system, it means you are going to evaluate all the parameters. All the parameters till now we have studied. So in this case, if we are going to equate a second order system, of course, for this one we have already given an input is a unit step and order of the system is 2. So it means we can equate this one. And from here we can find out omega n is nothing but under root of 8. So it comes out to be 2.83 radian. Now 2 times zeta into omega n. Sorry, this one is 2 times zeta into omega n. Is nothing but 4 times 4. And we know that omega n is 2.83. So if we are going to calculate zeta, it comes out to be 0.7067. It is an underdamped system. And what about omega d? It's omega n under root of 1 minus zeta square. If we are going to calculate it, it comes out to be 2.002 radian. Now, for example, I mentioned you that you have to calculate the transient response. So now you have to calculate each parameters. First one is Tp. Tp is nothing but pi by omega d, and omega d is pi by 2.002. So it comes out to be 1.57 seconds. Now what is Mp? Mp is in percentage e to the power minus pi zeta under root of 1 minus zeta square and it into 100. If you are going to fill the value of zeta, which in our case is 0.7067, then it comes out to be 4.33%. Now settling time 4 upon zeta into omega n. If nothing is mentioned in your question, that for example we are not mentioning you the specified range, then you have to assume it plus minus 2%. And it comes out to be 2 seconds, everything you know. Then what is Ct? Ct is nothing but 1 e to the power minus zeta into omega n t upon under root of 1 minus zeta square, and this one is sine of omega dt plus theta, and everything you know. The only thing that you have to calculate is tan inverse under root of 1 minus zeta square upon zeta, and that comes out to be pi by 4 radian. Now you can fill up, then you can find out what is Ct. ये point clear है? If you want to calculate what is time constant, it is nothing but zeta upon omega n. If you want to calculate what is delay time, even though you have a formula for that one, and the delay time is time delay is 1.1 this one zeta upon omega n. In that case, you can also derive it from Ct, that 50% of the output. Then put it Ct is equal to 0.5 is equal to 1 minus e to the power minus zeta, and T is Td upon under root 1 minus zeta square sine of omega d t plus theta. So now if you have any doubt, please ask me. So now you will have to practice. So in the next lecture, we are only going to deal with the questions, different kind of questions, that how we are going to solve those questions. But I assume that all of you have a knowledge about block reduction diagram, because we, for example, I'm going to give you a one block, and which consists number of different blocks. So first we are going to find out the transfer function from using the block reduction technique, and then we are going to calculate the time response and steady state error. Now, if you have any question, please ask me. सिद्धांत,
Yes, sir.
कुछ पूछना है?
No, sir.
अभी
Yes, sir.
कुछ डाउट है बेटा?
No, sir.
The only thing that you have to remember, it is a second order system and the input response is a unit step. Then you have to remember that formula and you have to put the conditions. See, what is the 50% peak time? So maximum we are going to achieve at the peak time. So you can put that one, that dCt by dt at t is equal to Tp must be equal to 0. Similarly for the guys, peak overshoot, the maximum I got. Even in the case that we have put this 0.98, you can also take 1.02 and you are going to get the same answer. That is 4 upon zeta into omega n for the settling time. And if I didn't mention that what is the percentage of error that you have to be taken, then you are going to consider plus minus 2%. Most of the time I found it in the examination that people are writing that 3 upon zeta into omega n. That is only true for the 5%. If I didn't mention, then you have to calculate only for the plus minus 2%. So if you are going to calculate it for the 5%, I'm not going to give you a marks. Okay, so now I'm going to end this lecture.